I am Jeannette Wing, Evanescience Director of Data Science and Professor of Computer Science at Columbia University. I'm also an adjunct professor of computer science at Carnegie Mellon University. I want to talk to you about a new research program I'm promoting called Trustworthy AI. For certain tasks, AI systems have achieved good enough performance to be deployed in our streets and our homes. Object recognition helps modern cars see. Speech recognition helps personalized voice assistants converse. For other tasks, AI systems have even exceeded human performance. AlphaGo was the first computer program to beat the best Go player in the world. The promise of AI is huge. They will drive our cars. They will help doctors diagnose disease more accurately. They will help judges make more consistent court decisions. They will help employers hire more suitable job candidates. But why should we trust AI-based systems? We know these AI systems can be brittle and unfair. Adding graffiti to a stop sign fools the classifier into saying it is not a stop sign. Adding noise to an image of a benign skin lesion fools the classifier into saying it is malignant. Risk assessment tools used in the US court system have shown to be biased against Blacks. Corporate recruiting tools have shown to be biased against women. So the question I pose to the community is, how can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? I come from a background of formal methods and trustworthy computing. And so in the remainder of my talk, I want to show how AI systems up the ante in terms of adding new properties for trustworthiness that we need to think about in the trustworthy computing community, and demanding new specification and verification techniques in formal methods in order to assure trustworthiness of AI systems. So let me talk about how we go from trustworthy computing to trustworthy AI. In trustworthy computing, which has been around for a couple decades now, we have come to agree that the properties of trust we care about are reliability. Does it do the right thing? Safety. Does it do no harm? Security. How vulnerable is it to attack? Privacy. Does it protect a person's identity and data? Availability. Is the system up when I need to access it? Usability, can a human use it easily? And it is some kind of computing system made up of hardware, software, and of course the people who interact with the system. From trustworthy computing to go to trustworthy AI, we're upping the ante in terms of the kinds of properties that we need to assure for trustworthiness of an AI system. Of course, we still want to build on the trustworthy computing properties as before, but we're adding new properties that are germane to AI systems. Also, the system that is of concern is not just the hardware and the software and the people engaged in this computing system, but the nature of an AI system begs us to talk about the data used to train a machine learning model, the machine learning model itself, and the task that this machine learning model and the AI system is supposed to perform. So let me talk a little bit more about these additional properties. Accuracy. How well does the AI system do on new unseen data compared to data on which it was trained and tested? Robustness. How sensitive is the outcome to a change in the input? Fairness, are the outcomes unbiased? Accountability, who or what is responsible for the outcome? Transparency, Is it clear to an external observer how the system's outcome was produced? Interpretability, explainability. Can the system's outcome be justified with an explanation that a human can understand and/or that is meaningful to the end user? Ethical. Was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And there may be properties that we have yet to define and identify and define. So the question then, how can we achieve trustworthy AI, is a wide open question. And one approach I want to advocate is through formal methods. So now I want to explain how I see trustworthy AI upping the ante on the formal methods community. In traditional formal verification, we frame the problem as, does M satisfy P? Where M stands for a program or piece of code, a protocol, or an abstract model of a concurrent or distributed system. It's a formal object. The double turnstile represents the logical framework in which we do the verification. So we have logics, and then we have tools that implement those logics to help us scale up the logical reasoning needed to do the verification. So these tools are tried and true and have shown practicality. They include model checkers, theorem provers, and SMT solvers. And P is simply the representation in a formal language of the property we care about, the property we want to verify of M. And this P is usually expressed as some kind of formula in Boolean logic. And for instance, for concurrent and distributed systems, we might use temporal logic to express safety and liveness properties. We sometimes add explicitly the assumptions about the system, about the environment in which the model or the system operates. We express these assumptions by modeling E, the environment, or explicitly writing down the constraints of M as the assumptions in the environment, of the environment. So what about verifying AI systems? Well, here's how we're upping the ante. First of all, I want to start with a similar framework. Does M satisfy P? But here we need to reinterpret M as possibly a machine learned model, not just the whole AI system, which is a piece of code running in some uncertain environment. But in the end, it is a piece of code, which gives me hope that we can borrow for formal methods to address how to verify AI systems. The double turnstile suggests potentially new logics or new logical frameworks and even new mathematics that we might need to do the verification. We might, for instance, given the probabilistic nature of M, need probabilistic logics. And finally, P is very likely to be a formula written in a probabilistic logic or refer to expressions that are not easily formalizable in a discrete Boolean logic. Perhaps most interestingly, I'd like to introduce the notion of D, which has the analog of the E, the explicit assumptions about the environment of M in traditional formal verification, where D stands for a model of data. So this data could be the data that we use to train and test the machine learned model, but more importantly, it has to represent the data in which we intend to deploy the machine learning model. This, by definition, is data we have not seen, but data that is going to be relevant to determining whether M satisfies P. So a kind of representation for D might be a stochastic process or distribution that generates the data inputs on which M's outputs need to be verified. So this is the framing of the trustworthy AI problem from a formal methods perspective. And now in my remaining time, I want to walk through some of the outstanding challenges in trying to formalize D, M satisfies P. Let me first point out two main differences in trying to show this formula holds. First, I argue we need probabilistic reasoning. Second, the role of data seems particularly novel and important in showing any kind of verification of a machine learned model or an AI system. And for this talk, I'm really only going to talk about two important insights that are relevant to the role of data in this verification problem. But let me start with arguing the need for probabilistic reasoning. First, M is semantically and structurally different from a typical computer program. M is inherently probabilistic. Internally, the model itself operates over probabilities and outputs results with assigned probabilities. Structurally, M is machine generated, and it's unlikely to be human readable. In fact, from a programming language point of view, one can think of it as another kind of intermediate code. P may be formulated over continuous, not just discrete domains, and/or using expressions from probability and statistics. For example, robustness properties for deep neural networks are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. Differential privacy is defined in terms of a difference in probabilities with respect to a very small real value. And the logical frameworks I believe we're going to want to borrow from come from probabilistic logics and hybrid logics, which of course we have a long history of studying because of hybrid systems and cyber-physical systems. But we need these logics for our verification task at hand to be scalable, and we may need new verification techniques that work over reals, nonlinear functions, probability distributions, stochastic processes, and so on. Now, what about the role of D? First, I want to distinguish between what I call available data, data at hand used for training and testing a machine learned model, and unseen data, data over which M needs or is expected to operate without having seen it before. I will skip through this question, the research challenges of collecting and partitioning data, which you can read in my blog post, and talk specifically about specifying D, specifying unseen data, D. How do we specify the data and characterize properties of the data D? We could, as I mentioned before, specify D as a stochastic process or data distribution. We could use probabilistic programming languages, for example, STAN, which is used to specify statistical models. But what of large real-world data sets that do not fit common statistical models or which have thousands of parameters? I think this is a research challenge. There's another challenge that I mull over, which is breaking the circular reasoning. To specify unseen data, we need to make certain assumptions about the unseen data. Would those assumptions not then be the very same we would make to build the model M in the first place? In other words, how can we trust the specification of D? Now, this is not a new problem in formal methods. We need to trust the specification of the assumptions, for instance, E, that we make of the environment in which M, the system that we care about to verify, will be deployed. But here's some approaches that we can use to break the circular reasoning. First, there's a repertoire of statistical tools that we can use to validate our specification of D. Second, we could start small and assume that an initial specification is simple enough that it can be checked by, say, manual inspection, and then use a iterative refinement process akin to counterexample guided abstraction and refinement in formal methods to bootstrap from this initial specification to get something more realistic. And another question in terms of the question of specifying unseen data is, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? I want to point out another question that I mull over, which is the question of what do we quantify over? In traditional formal methods, we strive to prove for all x, p of x, where we might mean for all values of input parameter x, we want the property p to hold. Or we might want to say for all execution sequences of a concurrent or distributed system, we want some property to hold. But in AI systems, we do not expect M to work for all input data or for all data sets D. So what do we quantify over? How can we specify the class of distributions over which P should satisfy, should hold for a given M? This might be property dependent. So for instance, for robustness in the adversarial machine learning setting, we might want to show that M is robust to all norm-bounded perturbations D. So that is not a single distribution, and it's not for all distributions, but it's for a class of distributions. More interestingly, we might want to show M is robust to all semantic or structural perturbations for the task at hand. For example, computer vision. In this particular case, we might want to make sure that it's not just adding any old noise, but adding noise that will make the classifier robust, but where that adding noise makes sense to doing object recognition. Here's another example. For fairness, we might want to show the machine learning model is fair on a given data set and all unseen data sets that are similar for some notion of similar. So right now, a lot of work in fairness in machine learning is showing that we train a machine learning model on a particular input distribution, and we want it to be fair on that input distribution. But that's not really how this machine learning model might be used in practice. We actually want this machine learning model to be fair for distributions of the future. And those distributions may be very different from those in which we use to train the model in the first place. And this is not an easy task to accomplish. Some very recent work that my colleagues and I just published in NeurIPS of 2020 shows how easy it is to build a fair classifier that is not robust. And what we show is a way to use an online algorithm to build a fair classifier that is robust with respect to a class of distributions. I'm only going to briefly flash this slide up to show that there are many questions dealing with the task of verification itself. Once we have a specification of D, we have a given model M, and we have this formal specification of a property, then we actually have to do the verification in our logical framework. Now, there are many other opportunities for formal methods that I didn't cover. As I mentioned, for an AI system today, AI systems are deployed to solve a particular task at hand. So can we take that task information and use that to guide our verification process? Another aspect of formal methods that I would like to advocate that we should think about is designing and building a machine learning model to be correct by construction. And this is the idea of constraining the development of a machine learning model with the very property which we would want to prove of it in a post facto verification. And this is a very hot area of research right now. Another question that we would like to be able to address is compositionality. What we like to be able to do is do small proofs of small entities and be able to build those entities, to put those entities together and compose the proofs to know that we still have some property at the global level. And finally, the statistical methods that I alluded to before can help us in evaluating our models and checking our models. And these techniques include sensitivity analysis, prediction scoring, predictive checking, residual analysis, and model criticism. These are all active areas of research and common techniques in statistics. So I will close by just saying the framing that I like for Trustworthy AI makes explicit the role of data in building AI systems and requires new thinking, new logics, new logical frameworks, and new methods and tools that support the foundations of this Trustworthy AI verification question. Thank you very much.